Welcome to the Deep Dives, where we, try to make complex stuff clear and give you that shortcut to being genuinely informed. Today, we're diving deep into the world of molecules, the tiny building blocks of everything. But we're actually starting somewhere maybe unexpected. Levitation. Did you know that, well, everyday objects, even like a strawberry or a frog, can actually levitate if the magnetic field is strong enough?
It really does sound like magic, doesn't it? But it's pure physics. It's not sci-fi at all. It's this fundamental property called diamagnetism. Basically, every material, wood, water, plastic, you name it, has electrons. And when you stick these materials in a strong external magnetic field, those electrons kind of shift their movement slightly. And this creates a tiny, tiny magnetic field of their own. And here's the crucial bit. That tiny field always pushes back. It opposes the external field.
Okay, so if that pushback force is strong enough, it overcomes gravity and just lifts the object.
Exactly.
Our sources mentioned this experiment back in '97, I think, at Radboud University in the Netherlands.
Oh, yeah, the famous one.
They apparently levitated hazelnuts, strawberries, and yes, even frogs, using a 16 Tesla field, which is huge. Pretty wild to picture a floating frog.
It definitely is, and it perfectly illustrates the power of these magnetic forces, even on things we don't think of as magnetic. And this whole phenomenon, biomagnetism, this almost magical levitation thing, it's actually the bedrock principle behind one of the most powerful tools in organic chemistry, nuclear magnetic resonance spectroscopy, NMR.
Okay, NMR. Let's unpack that then. So our mission for this deep dive is to show you how NMR uses these exact magnetic principles to figure out the precise structures of molecules, right down to the atom level.
That's the goal. We'll look at both proton NMR, that's HAH&M, and carbon-13 NMR.
We'll break down the key ideas, how chemists actually use it, solve puzzles with it.
Yeah, think of this as your guide to how chemists essentially see molecules. We'll hit some surprising facts, some really practical stuff.
All right, let's start at the beginning. The core idea.
Yeah.
This invisible dance of the atomic nuclei. NMR, fundamentally, is about how electromagnetic radiation interacts with atomic nuclei.
Right, but importantly, not all nuclei interact in a way NMR can see. You need a specific property called nuclear spin. Only nuclei with an odd number of protons or an odd number of neutrons or both have this spin.
Okay, so like a hydrogen nucleus. It's just one proton, so it has spin.
Perfect example. And carbon-12, the common carbon, it doesn't have spin, but its isotope, carbon-13, which has an extra neutron making an odd neutron number, does have spin. You can sort of picture this spinning nucleus generating its own tiny magnetic field, like a microscopic bar magnet.
So you got all these tiny nuclear magnets inside your sample. What happens when you put them into a big, powerful external magnetic field, like in an NMR machine?
Well, they don't just point randomly. Quantum mechanics kicks in, and they can only align in two specific ways relative to that external field, either with the field, which we call the alpha state, that's the lower energy state, or against the field, the beta state, which is higher energy. Only those two options. Think heads or tails.
And there's an energy difference between those two states, right? A specific gap.
Exactly, a precise energy gap. And here's where resonance comes in. If a nucleus in that lower energy alpha state absorbs a photon, a packet of energy that has exactly the right amount of energy to bridge that gap, it flips. It jumps up to the higher energy beta state. That absorption is resonance.
Good point to clarify. This resonance is totally different from the resonance structures we draw from molecules, like benzene rings showing electron movement.
Completely different concept, yeah. In NMR, resonance is just the specific absorption of energy causing a spin flip, and the energy needed falls smack in the radio wave part of the electromagnetic spectrum, low energy waves.
Now, you said earlier that if all protons absorbed the same frequency, NMR wouldn't be very useful, so...
What of it? This brings us right back to diamagnetism and those levitating strawberries. It's all about the electrons surrounding the proton.
Okay. How so?
Remember how the electrons create their own little magnetic field that opposes the external one?
Yeah, the shielding effect.
Precisely. That electron circulation shields the proton nucleus from the full strength of the external magnetic field. The nucleus experiences a slightly weaker net field.
So, different protons in a molecule are surrounded by different amounts of electron density.
Exactly. Some protons are near electron withdrawing groups, so they have less electron density around them. Others might be in electron-rich areas. This means they experience different levels of shielding. Different shielding means slightly different energy gaps between their alpha and beta states.
And different energy gaps mean they absorb slightly different radio frequencies to achieve resonance.
You got it. That variation is the magic. It's what lets us distinguish protons in different chemical environments. It's the foundation of NMR analysis.
Okay, so how do we actually measure these tiny differences? Modern NMR machines sound pretty complex.
They are. They use incredibly powerful superconducting magnets, cooled way down with liquid helium, to create a very strong, very stable magnetic field. Then, instead of slowly sweeping frequencies, modern FT-NMR Fourier transform NMR hits the sample with a short, powerful pulse containing all the relevant radio frequencies at once.
So it excites everything simultaneously.
Yes. All the different types of nuclei absorb their specific resonant frequencies from that pulse and flip. Then, as they relax back down, they emit faint radio signals. The machine detects this combined signal called the free induction decay, or FID. It looks like a mess, just a decaying wave.
Doesn't sound very useful like that.
Not directly, no. But then a computer performs a mathematical operation called a Fourier transform on that messy FID signal, and that magically converts it from signal intensity versus time into signal intensity versus frequency. And that's your NMR spectrum, peaks at different frequencies corresponding to different nuclei.
Clever. And doing it this way, with the pulse, means you can collect data much faster and average many scans to improve the signal, especially for things like carbon-13, which are rare.
Precisely. It boosts sensitivity enormously.
One more practical thing to solve it. If you dissolve your sample in regular chloroform, say, wouldn't the proton signals from the chloroform just swamp everything?
Absolutely. That's why we use deuterated solvents. We replace the hydrogen atoms in the solvent with deuterium, which is hydrogen 2. Deuterium nuclei have spin, but they resonate at a totally different frequency range than protons. So for a proton NMR experiment, they're effectively invisible. Chloroform, D-arrow, DMSO, D-arrow, standard practice.
Makes sense. Okay, so we've got our spectrum. What's the first piece of information we pull from it?
The first clue is simply the number of signals. How many distinct peaks or groups of peaks are there? That number tells you directly how many different kinds of protons are in your molecule. Protons in the exact same chemical environment are chemically equivalent, and they all contribute to the same signal.
How do you know if protons are equivalent? Is it just about being on the same carbon?
Not always. Symmetry is key. If you can mentally swap two protons through a rotation of the molecule or reflection through a mirror plane, and the molecule looks identical, they're often equivalent. We talk about homotopic protons, interchangeable by rotation, and enantiotopic protons, interchangeable by reflection. In standard NMR solvents, both these types usually give one signal.
What about ones that aren't equivalent?
Those are called diastereotopic. If swapping them creates a diastereomer, they are in different environments and will give different signals. This often happens to the two protons on a CH group if there's a chiral center nearby.
Okay, rules of thumb.
Yeah, the three protons on any methyl group, CH, are pretty much always equivalent. The two protons on a methylene group, CH, are usually equivalent, unless there's a chiral center nearby or some kind of restricted rotation.
You mentioned dynamic processes earlier. The cyclohexene example is fascinating. One signal at room temp, but two when it's cold.
Right. At room temperature, cyclohexane rings are rapidly flipping between two chair conformations. A proton that's axial in one moment becomes equatorial the next, and vice versa. The NMR measurement is relatively slow compared to this flipping. It's like taking a long exposure photo of a moving object. Everything gets blurred into an average. So you see one signal representing the average environment.
But when you cool it way down.
To about minus 100 Celsius, yeah. The flipping slows down dramatically. Now, the NMR camera shutter is fast enough to capture the distinct axial and equatorial protons before they flip. So you see two separate signals.
That's incredible. It shows NMR isn't just static structure. It can probe motion and kinetics, too.
Absolutely. It's a powerful tool for studying reaction rates and conformational changes.
Okay, so number of signals is clue 1. Clue 2. Where does the signal appear on the spectrum? The chemical shift.
Exactly. Chemical shift, symbol delta. It's measured in parts per million, ppm. This ppm scale is crucial because it makes a measurement independent of the magnet strength. A proton's chemical shift will be the same ppm value whether you use a 60 megahertz or a 600 megahertz machine.
And it's measured relative to a standard.
Yes, usually tetramethylsilane, TMS. It's a compound with 12 highly shielded equivalent protons, chosen because its signal appears far upfield, away from most other organic signals. We define its signal as 0 ppm.
We hear terms like downfield and upfield. What do they mean?
Downfield means higher ppm values, further to the left on a standard spectrum. Upfield means lower ppm values, towards TMS at 0 ppm on the right. Protons that are deshielded, meaning they feel more of the external magnetic field, resonate at higher frequencies and appear downfield. Protons that are shielded, feeling less of the external field, resonate at lower frequencies and appear upfield.
And what causes this shielding or deshielding? You mentioned electrons.
The biggest factor is usually the inductive effect of nearby electronegative atoms. Atoms like oxygen, nitrogen, or halogens pull electron density away from neighboring atoms, including protons. This withdrawal of electrons reduces the shielding around the proton. Less shielding means it feels more of the external field, requires higher energy, higher frequency to resonate, and thus shifts downfield to a higher ppm value.
And this effect falls off with distance.
Oh yeah, drastically. It's strongest for protons directly attached to the carbon bearing the electronegative atom, alpha protons, weaker for the next set, beta protons, and usually negligible after that.
Can we get some ballpark figures, like where do typical protons show up?
Sure. For a basic alkane environment, far from weird stuff, methyl protons, CH, are typically around 0.9 ppm, methylene, CH, around 1.2 ppm, methane, CH, around 1.7 ppm. Those are good starting points. Then you adjust. Being next to an oxygen and an alcohol or ether, that might add about 2.5 ppm next to a carbonyl group. Maybe add 1 ppm. It's additive, roughly speaking.
Okay, inductive effects. What else affects chemical shift? You mentioned pi electrons earlier.
Right, anisotropic effects. This is where the magnetic field generated by circulating pi electrons in double bonds or aromatic rings comes into play. It's a bit more complex than simple induction. The circulating pi electrons create their own local induced magnetic field. Depending on where a proton sits relative to this induced field, it can be either strongly shielded or strongly deshielded.
And the classic example is benzene, right? Aromatic protons.
Exactly. The pi electrons in a benzene ring circulate in the presence of the external field, creating a ring current. This current generates an induced magnetic field that adds to the external field outside the ring, where the protons are. This strongly deshields the aromatic protons, pushing their signals way downfield, typically around 7 to 8 ppm. It's a very characteristic region.
And this ring current idea wasn't just a guess, right? It helped confirm the whole concept of aromaticity.
Absolutely.
Yeah.
NMR provided direct experimental evidence for this special electronic behavior. It was crucial. And you see similar effects elsewhere. Aldehyde protons, the H on CO, are also very deshielded by the pi electrons of the carbonyl group, typically showing up way downfield around 9-10 ppm.
So we have number of signals, how many kinds of H, chemical shift, their electronic environment. What's clue number 3?
Clue number 3 is the size of the signal. More specifically, the area under the signal peak or peak group. This is called the integration.
And what does the integration tell us?
It tells you the relative number of protons that are creating that signal. If one signal has twice the area of another, it means there are twice as many protons contributing to the first signal compared to the second.
So the raw numbers from the machine aren't absolute proton counts?
No, they're relative ratios. The spectrometer might spit out numbers like 21.3 and 32.0. You divide both by the smaller number, so 21.3, 21.3 equals 1. And 32.0, 21.3 is about 1.5. So the simplest whole number ratio would be 2 to 3.
But that 2.3 ratio might not be the actual number of protons, right?
Exactly. That's a crucial point. You need the molecular formula. If your formula tells you there are 10 protons total in the molecule, then that 2.3 ratio must actually represent 4 protons and 6 protons, since 4 plus 6 equals 10, and 4.6 simplifies to 2.3. This also helps spot symmetry.
Okay, very important distinction. Number of signals, chemical shift, integration. There's one more piece, isn't there? The shape of the signal.
Yes, the fourth and often most informative clue, the multiplicity or splitting pattern. This is about whether a signal appears as a single peak, a singlet, 2 peaks, a doublet, 3 peaks, a triplet, 4 peaks, a quartet, and so on.
What causes a signal to split like that?
It's caused by the magnetic fields of neighboring non-equivalent protons. It's called spin-spin splitting or coupling.
Okay.
Essentially, the spin state, alpha or beta, of a neighboring proton slightly changes the magnetic field experienced by the proton you're looking at.
So the neighbors influence the signal.
Yeah, they talk to each other magnetically. If a proton has one non-equivalent neighbor, that neighbor can be either spin alpha or spin beta. This creates 2 slightly different magnetic environments for the proton we're observing, so its signal splits into 2 peaks of equal intensity, a doublet.
And if it has 2 neighbors?
If it has 2 equivalent neighbors, there are 3 possibilities for their combined spins, both alpha, 1 alpha, beta, both beta. This splits the signal into 3 peaks, a triplet with an intensity ratio of 1.2.1. 3 equivalent neighbors, 4 possibilities, splits the signal into a quartet, ratio 1.3.3.1.
Ah, so this leads to the famous M+1 rule.
Exactly. If a proton or group of equivalent protons has an equivalent neighboring protons, its signal will be split into n+1 peaks.
Are there rules about which protons can split each other?
Yes. Q rules. 1. Equivalent protons do not split each other. The protons within the same CH years group, for instance, don't split themselves. 2. Splitting usually occurs between protons separated by 2 or 3 sigma bonds, called geminal and vicinal coupling, respectively. Splitting over longer distances can happen, but it's often weaker or 0.
Okay. And the distance between the peaks in a multiplet, that means something too.
It does. That distance is the coupling constant J, measured in hertz, not ppm. The J value represents the strength of the magnetic interaction between the coupled protons. What's really useful is that the J value is independent of the spectrometer's magnetic field strength. Protons that are coupled to each other will have the same J value. This helps you identify which protons are neighbors.
And you mentioned higher field magnets give clearer spectra. How does the J value relate to that?
Because the chemical shifts in ppm spread out more at higher field strength, while the J values in hertz stay the same. So at higher fields, the splitting patterns are less likely to overlap with each other. A 7 Hz coupling is a smaller fraction of the total spectrum width at 600 MHz than at 60 MHz, making multiplets much better resolved. Less clutter.
Got it. Learning these patterns must be key to solving structures.
Absolutely. Pattern recognition is huge. See a triplet integrating to 3 protons next to, well, slightly downfield of a quartet integrating to 2 protons. That's the classic signature of an ethyl group.
Or like an isopropyl group.
Yep. That's typically a doublet integrating to 6 protons, the 2 equivalent CH groups, upfield of a septet 7 peaks, integrating to 1 proton, the CH. Or a tert-butyl group. That's just a singlet for 9 protons because the methyl groups have no neighbors on the adjacent carbon.
What if a proton has neighbors that aren't equivalent to each other? Does the N+1 rule still work?
Good question. That's where it gets complex. If a proton is coupled to, say, 2 neighbors of type A with coupling J and 1 neighbor of type B with a different coupling J, then its signal first splits into a doublet, due to B, and each peak of that doublet splits again into a triplet, due to A. You'd call it a doublet of triplets. Sometimes, if the J values are very similar, these complex patterns can merge and just look like a messy blob, which we often just call a multiplet.
Are there protons that sometimes don't follow the splitting rules?
Yes, the most common culprits are protons on heteroatoms, like the H in an alcohol, OH, or an anenine, NH. These protons often participate in rapid chemical exchange with each other or traces of water acid. This exchange happens faster than the NMR measurement, so the proton doesn't feel the spin state of its neighbors consistently. The coupling gets averaged out, and you usually just see a broad singlet for the OH or NH proton.
Do you ever see the coupling?
Sometimes, yes. If you run the sample very pure and dry, or sometimes by cooling it down, you can slow the exchange and see the expected splitting. Also, aldehyde protons, even though they have neighbors, often show up as singlets or very small doublets because the coupling across the CO system is typically very weak.
Okay, wow. So we have these 4 key pieces of info. Number of signals,
Yep.
chemical shift, integration, and multiplicity.
Yeah.
Now, how do we put it all together? Become molecular detectives.
It really is like detective work. There's a general strategy. Step 1, if you have the molecular formula, calculate the hydrogen deficiency index, HDI, also called degrees of unsaturation. It tells you the total number of rings and more pi bonds. An HDI of 4 or more strongly suggests an aromatic ring is present. Big clue.
Step 2.
Look at the number of signals and their integration. Does the number of signals match the number of carbons? If not, there's probably symmetry. Do the integration ratios add up to the total number of protons from the formula?
Step 3. Analyze each signal in detail.
Exactly. For each signal, what's its chemical shift? What kind of environment? What's its integration? How many protons? What's its multiplicity? How many neighbors? Use this info to propose small molecular fragments like, this triplet quartet pattern means I have an ethyl group, or this signal at 7.2 ppm looks like aromatic protons. These are your puzzle pieces.
Step 4. Assemble the pieces.
Yep. Fit the fragments together in a way that makes chemical sense and satisfies all the connectivity implied by the splitting patterns. Remember, if proton A splits proton B, they must be neighbors.
And the final, crucial step.
Verify. Double-check that your proposed structure is completely consistent with every piece of data in the spectrum. Does the chemical shift make sense for every proton? Does the splitting match the neighbors in your structure? Does the integration match?
Let's take that example from the source. HEI calculation gives 5. That's high. Maybe a ring plus some double bonds.
Good start. Then maybe the spectrum shows signals around 7-8 ppm integrating to 5 protons.
Okay, 5 aromatic protons. That screams monosubstituted benzene ring. That accounts for CH euro and an HEI of 4.
Right. What's left? CH euro and one more HDI unit. Maybe you see a singlet way downfield around 10 ppm integrating to 1 proton.
10 ppm, singlet, aldehyde, the CHO.
Yeah.
That uses up CHO and the last HDI unit, the COO pond.
Now we have CH euro left. Maybe the spectrum shows 2 triplets, each integrating to 2 protons, around, say, 2.53 ppm.
2 triplets, each 2H. That look like CH euro. They're triplets because each CH group sees the other CH group as neighbors. N2, so N plus 1 to 3 triplet.
Exactly. Now, put the pieces together. CH, a CH euros, and a CHO. The only way that fits is FeH, CH0, CHO. 3 phenyl propanol.
And then you check, does this structure explain all the shifts and splitting? Yep. Seems consistent. Brilliant.
It's a powerful process, and NMR is fantastic for telling similar compounds apart too, like isomers. Even if they have the same number of signals, there will almost always be some difference, a shift, an integration detail, a coupling constant that lets you distinguish them.
And this isn't just academic. You mentioned the FDA using it for drug safety with heparin.
Yeah, a really important real-world example. Heparin is a vital blood thinner. Pure heparin sodium has a specific OPLN-H NMR spectrum, including a clean singlet just above 2 ppm. But some contaminated batches, which sadly caused serious adverse reactions years ago, showed extra signals near that 2 ppm region, revealing the presence of a dangerous impurity. NMR was key to identifying the problem and ensuring safer supplies. Quality control is a huge application.
Okay, we've covered proton NMR in detail. What about its partner, NTT NMR? Looking at the carbon skeleton.
Right, NTC NMR. Same basic principles, nuclear spin, magnetic fields, resonance, but some key practical differences. The biggest hurdle is that the NMR active isotope, carbon-13, is only about 1.1% of natural carbon. Carbon-12, the other 99%, is invisible to NMR.
So the signals are much weaker.
Much, much weaker. You need more sample, longer acquisition times, and sensitive detectors. It's inherently less sensitive than proton NMR.
And you said the interpretation is simpler, only chemical shift usually.
Generally, yes. For standard course-use spectra, we mostly focus on the chemical shift. Integration isn't usually reliable for ORCC because of relaxation effects and the way the spectra are acquired. And splitting is usually removed.
Removed? How? You mean ORC splitting?
Well, EC splitting is incredibly rare because the chance of 2C atoms being right next to each other is tiny, 1.1% times 1.1%. So you almost never see that. What you would see is splitting caused by attached protons, AC splitting, which would make the spectrum incredibly complex. Imagine every carbon signal split by its 1, 2, or 3 attached protons.
That sounds like a nightmare to interpret.
It is. So standard UC NMR uses a technique called broadband proton decoupling. While acquiring the ECC data, the instrument continuously blasts the sample with all the proton resonance frequencies. This rapidly flips the proton spins back and forth, effectively averaging out their magnetic effect on the carbons. It decouples them. The result: each chemically distinct carbon atom typically shows up as a single line, a singlet. Much cleaner.
Okay, so a standard Prussian spectrum gives you singlets. The number of singlets tells you the number of different types of carbon atoms.
Exactly. Symmetry still counts. Equivalent carbons give only one signal, and the chemical shift tells you about the carbon's environment.
Is the chemical shift range similar to proton NMR?
No, it's much wider. While proton NMR typically spans 0-12 ppm, OMIO-C NMR covers about 0-20 ppm relative to TMS, which is also the zero reference for carbon. This wide range means signals are usually well separated.
Are there typical regions, like for protons?
Definitely. Alkyl carbons, so hybridized in alkane-like environments, are usually furthest upfield, maybe 0-50 ppm. Carbons next to electronegative atoms like oxygen or halogens, or spuit hybridized carbons in albanes, tend to fall in the 50-100 ppm range. Then you get the spoke carbons. Alkene and aromatic carbons typically resonate between 100 and 150 ppm. And furthest downfield, highly deshielded, are the carbonyl carbons, so CO, from ketones, aldehydes, acids, esters. They're usually found way down between 150 and 220 ppm. Very characteristic.
But wait, if the standard spectrum just gives singlets, you lose the information about how many hydrogens are attached to each carbon, right? That seems important.
It is, and you're right. The broadband decoupled spectrum doesn't give you that directly. That's where special techniques come in, most commonly DPT and MR.
DPT, what's that stand for?
Distortionless enhancement by polarization transfer. Fancy name, but what it does is pretty neat. DPT experiments use specific pulse sequences to manipulate the signals based on how many protons are attached to each carbon. You run a few different DBT experiments along with the normal broadband decoupled spectrum.
Okay, what do the different experiments show?
You get your normal spectrum showing all carbon signals as positive peaks. Then you run a DPT90 experiment. In this one, only CH carbons, methenes, show up as positive peaks. Cs, CH, and quaternary carbons, C with no H, are absent. Then you run a DPT135. Here, CH and CH carbons give positive peaks, pointing up, but CH carbons give negative peaks, pointing down. Quaternary carbons are again absent.
I see. So by comparing the three spectra, the normal one, DPT90 and DPT135, you can figure out what each peak represents.
Precisely. If a peak is present in all three, positive in normal and DPT135, also positive in DPT90, it must be a CH. If it's positive in the normal and DPT135, but absent in DPT90, it's a CH. If it's positive in the normal spectrum, but negative in DPT135 and absent in DPT90, it's CH. And if it's present in the normal spectrum but absent in both DPT90 and DPT135, it must be a quaternary carbon.
That's really clever. It gives you back that vital proton count information without the complexity of a fully coupled spectrum.
Exactly. WT is an essential tool for IOC assignment.
Now, taking this whole NMR idea to a much bigger scale, MRI machines in hospitals, that's basically NMR, right? But on people.
That's exactly what it is, magnetic resonance imaging. It's fundamentally NMR spectroscopy applied to imaging the human body. It's a huge NMR machine.
So instead of a chemical sample in a tube, it's, well, us. What nuclei is it looking at?
It primarily detects the H nuclei, the protons, because they are incredibly abundant in the body, mainly in water, H uro, and fat molecules. Different tissues have different amounts of water and fat, and the protons in these different environments relax at slightly different rates after the radiofrequency pulse.
So the machine can map out these differences?
Yes. By using gradient magnetic fields, it can pinpoint where the signals are coming from in 3D space. It measures the intensity and relaxation properties of the signals from each tiny volume element, voxel, of the body. A computer then reconstructs this data into detailed cross-sectional images. It can distinguish soft tissues like muscle, fat, brain matter, and detect abnormalities like tumors, inflammation, or, say, a ruptured spinal disc pressing on a nerve.
And it can even see things moving, like a heart beating.
It can, yes.
Yeah.
Techniques like cardiac MRI can time the image acquisition with the heartbeat to get clear pictures of the heart muscle and blood flow.
And crucially, it's considered very safe, right? No harmful radiation like X-rays or CT scans.
That's a major advantage. The strong magnetic fields themselves are considered safe, and the radiofrequency waves used are non-ionizing and harmless at the levels used. It's an incredibly powerful diagnostic tool with very low risk to the patient.
So from levitating frogs to mapping the human brain, it all comes back to these tiny nuclei spinning in magnetic fields. We've really covered a lot today.
We have. We went from the basic physics of nuclear spin and that diamagnetism effect all the way to interpreting the 4 key pieces of information in a light-adjacent spectrum number of signals: shift, integration, multiplicity, and how they combine to let you deduce a molecule's structure.
And then into EC-NMR, the importance of decoupling, and how DTP helps us figure out the carbon skeleton.
It's amazing how much information is encoded in those seemingly simple spectra. Understanding how to decode it is fundamental to modern chemistry and beyond.
It really makes you appreciate how chemists and physicists figured all this out, piece by piece. It's like learning a whole new language spoken by molecules.
It is, and it's a language that tells us not just structure, but also about dynamics, purity, and even helps diagnose disease, a testament to probing the fundamental properties of matter.
So next time you hear about a new drug, or maybe even get an MRI, you'll have a much deeper appreciation for the incredible power of magnets and radio waves, and that quiet dance of atomic nuclei making it all possible. What other hidden information, I wonder, is waiting to be unlocked just by observing these fundamental properties? Something to think about. Thank you for joining us on this deep dive.